Rudewright Academy. Learn it, teach it, remember it. Picture a phone book, a million names all in order. Read it straight through from the top and you would be here all day. Yet you can land on any single name in about 20 looks. Not 20,000, just 20 on the very same million names. And the whole difference comes down to one simple idea. Let me show you. You already do this without ever being taught. I am thinking of a number from 1 to 100, so guess. Almost everyone opens with 50. I say higher, and just like that, every number below 50 is gone. Not one by one, but all 50 at once from a single word. So you try 75. I say lower, and the whole top quarter vanishes too. You corner my number in about 7 guesses because every answer is worth half of everything still standing. Now the very same move on real data. Here is a sorted array, 12 cells from smallest to largest, and we are hunting for 23. Notice the one thing this whole trick rests on. The array is sorted. Order is the price of admission. It is the only reason a single glance at the middle can tell you which half to throw away. Shuffle the cells, and the magic dies instantly. The name itself gives away the mechanism. Binary, as in 2. Every step asks one two-way question. Is the thing I want below the middle or is it above? 2 possible answers, and each one is worth half the array, a single yes or no that cleaves the world in 2. First, the obvious way. Start at the left and check the cells one at a time. On 12 cells, no harm done. But grow the array and watch the counter climb. 1,000 cells means up to 1,000 checks. 1,000,000 means up to 1,000,000. Looking at everything costs exactly as much as there is to look at. That is the wall the clever idea must break, and it breaks it clean in half. Here is the turn, the whole video in one move. Because it is sorted, you look at just the middle cell. If what you want is bigger than what sits there, it cannot be anywhere on the left, not probably, it simply cannot. One look just erased half the array and you never even glanced at those cells. Order had already promised they were out. One question, and half the world is gone. To run that safely, we hold one promise the whole way down. The answer always lives between a low marker and a high marker. The window between them is the only place it can be. Each step we slide one marker inward, never past where the answer could be. Keep that promise, and the window can only shrink around the truth. Let us run it for real. Low at the far left, high at the far right. The middle is 16, too small, so 23 must be to the right and the entire left half drops away. New middle, 56, too big, so this time the right half drops. One cell is left standing, so do not let me tell you, you call it, where is 23? Right there, 3 looks on an array we would have scanned a dozen times. Here is the whole thing, just 9 lines. Keep a low bound and a high bound. While they have not crossed, look at the middle. If it is a match, you are done. Too small, and you lift the low bound just above the middle. Too big, and you drop the high bound just below it. If they cross with no match, the value was simply never there. Now the folklore. 9 in 10 programmers cannot write this bug-free on the first try, and the traps are always the same 3. 1. The midpoint. Add low and high together first, and in a fixed width integer that sum can overflow and wrap to a negative index. This exact bug sat inside a standard library for 9 years before anyone noticed. The fix is to walk half the gap up from the low bound instead. 2. The off by 1. If the middle cannot be the answer, step past it, and if it might be, keep it. Get that 1 backwards and the window stops shrinking so your program hangs forever. 3. The finish line. One version stops when the bounds cross, the other when they meet. Pick one and burn it into muscle memory because quietly mixing them breaks both. So where does all that speed come from? Each step halves what is left, and halves it again and again until a single item remains. That count, the number of halvings, is the logarithm. 1,000 items, 10 steps. 1,000,000, 20. 1,000,000,000, just 30. The data explodes, the work barely flinches. And notice, we did not assert that number, we counted it. Put them shoulder to shoulder on the same million. Linear search trudges off one cell at a time and keeps going and going. Binary search takes its 20 looks and it is already finished, sitting there waiting while linear is still crawling near the start. It is not a close race. It is not really a race at all. Now the half almost no one is taught where binary search stops being an array trick and becomes a way of thinking. New problem. You ship packages in order across 5 days, and you want the smallest boat that still finishes on time. There is no array anywhere in sight to search. But look harder. There is a sorted line hiding in the question. Every possible boat size from smallest to largest. Ask each boat one simple question. Does it finish in time? A tiny boat is far too slow, that is a no. A bit bigger, still a no. Then at some size it tips to yes, and here is the gift. Once it is yes, every larger boat is a yes as well. More room never hurts, so the yes spreads all the way to the right. Read along the line and you get no, 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 yes, 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 a single clean flip, which is exactly what binary search hunts for. So we search the boat sizes exactly the way we search the array. Try the middle size and run the shipping once. Does it finish in 5 days? If it does, we do not need a boat this big, so we drop the high bound. If it does not, we need more room, so we lift the low bound. Each guess runs one quick simulation and throws away half the sizes, and in about 30 guesses we land on the smallest boat that works, on a space we never built. That is the entire move, a recipe you can run on demand. 1. Name the answer as a single number on a range. 2. Pin the range, the smallest it could be and the largest it could be. 3. Write the yes or no test, and check that it flips only once. 4. Binary search the range with that test as the work at each step. Bound the range and write the test, everything else is the same 9 lines. Once your eye is trained, you see this shape everywhere, always the same sentence. The smallest or largest value where a yes or no test flips. The slowest eating speed that still clears the pile in time. The widest spacing that still fits every animal in the field. The square root, the biggest number whose square still fits underneath. Different stories, one skeleton, a sorted line of answers, and one honest test. 2 honest cautions before you reach for it. First, the test really has to flip just once. If it goes yes, then no, then yes again as the answer grows, there is no single boundary, and binary search will hand you a confident wrong answer, so check that first. Second, if the range is tiny or the test is slow and painful, do not bother being clever, just try every value. 2 pictures to carry out the door. The first, a sorted array and every look throwing away half, that is the logarithm, 1,020,000. The second is the bigger one. Anytime a question asks for the smallest or largest value where something becomes true, picture that no, 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 yes, yes, yes line and binary search the answer itself. The code was never the hard part. The skill is spotting the sorted line hiding in the question, and once you spot it, the code writes itself. Want to keep learning? Come find us at academy.rudewrite.com.